All right, so we're going to talk about the 2011 code. Whoop, there it is. 2011 NEC, and we're looking at section 240.87 of the NEC. This is the first introduction of an arc reduction requirement in the National Electrical Code outside of ground fault protection of equipment. So remember, the only two locations that we try to address an arc flash event in the National Electrical Code is 230.95, which was basically put into the National Electrical Code in 1971. And what was going on in 1971 at service entrance equipment, from a historical perspective, we were moving from a ungrounded systems, Delta ungrounded systems, to grounded systems because of the problems associated with ungrounded systems, fluctuations in voltages, damaging equipment, etc. So we moved from an ungrounded system to a grounded system. Now remember, in an ungrounded system as well, that first ground fault is a gimme, right? So we have requirements in the code for ungrounded systems that you need to have ground fault indication of where problems are in the power distribution system so that you know you have a ground fault, because that first ground fault is basically grounding the system. Now you have a corner grounded delta system or something similar, that type of a, not quite, but that type of an issue going on. You're grounding one of the phases. So somebody had the idea that, hey, I can get rid of these overvoltage fluctuations, which is damaging motors, the winding in motors, etc., by grounding the system. But then that introduced the fact that that first fault is a doozy, because now you already have grounded the system, and whenever you have a ground fault, it can be taxing on the power distribution system, to say the least. So the other thing that was happening back then, it was like 50s, 60s time frame, we were moving from 208 volt systems to 480 volt systems. And that's because motors and things, all your equipment was, there's a lot of different reasons. Your equipment was you have 480 volt straight rated equipment, but you had that before, but in any case, it was getting more prevalent. You needed to hire, they were raising the voltages, they were grounding the system, they were also the average size, because when you increase the voltages, your currents go down. The average service went from a 600 amp service to a 3000 amp or higher service. So you had the larger overcurrent protective devices, higher voltages, grounding the system, and the larger overcurrent and lower fault currents. So your arcing currents were in the long time region of these standard thermomagnetic breakers that we were seeing on the service equipment. So you were having arc flash events, very well documented issues. And so in 1971, they put a requirement for ground fault protection of equipment, because at that time, that was the only solution that we had as a technology to address that problem. So that was in 230.95. It made its way into 215 for feeders, in 210 for branch circuits, all related, though, to grounded systems greater than 208 volts and services. So then you had some requirements in 110 for marking. 110.16 in the 2011 code basically is a requirement for marking of the arc flash hazard warning. So what 110.16 tells us is electrical equipment such as switchboards, panel boards, industrial control panels, meter socket enclosures, and motor control centers that are in other than dwelling units and are likely to require examination, etc., have to be labeled with warning qualified persons of potential electrical arc flash hazards. Now, it said in the 2011, it says field marked. And the challenge that brings to the manufacturer is, some of these labels I will put on at the factory, because I know where it's going. I know it's not going to be in an area that's not going to require servicing. I know it's not going to be in a dwelling unit. But the problem is that this language in 110.16 says field marked. So you still have to, some inspectors will say, hey, you need to put that on a field. But the arc flash hazard warning is just that. It's a warning. So here in the 2011 cycle, Mr. Jim Dollard put a public input in for 24087. Now, what they were trying to address in 24087 were the circuit breakers that don't have an instantaneous. So the title of 24087 is Non-Instantaneous Trip. But if you really talk to those who are advocates of this, they understand that it's really not driven, the incident energy, the amount of energy at these locations is not driven by the fact that the circuit breaker doesn't have an instantaneous. It's driven by the fact that the arcing currents are not in the instantaneous region. And on very large breakers, you have a very high likelihood that the fault current is not going to be in the instantaneous region. And you will definitely have the likelihood that the arcing current is not in the instantaneous region when you have a circuit breaker that does not have an instantaneous trip. And what breaker is that possible on? All molded case circuit breakers will have an instantaneous trip. All insulated case circuit breakers will have an instantaneous trip. Why do I put an instantaneous trip in a circuit breaker? It is not because the UL standards require it. The reason I put an instantaneous on a circuit breaker is to protect itself. Think about what's the hardest job of a circuit breaker is not to open, because we leverage the magnetic forces to let it open. It's holding those contacts closed without chattering. We don't want chatter, because when you start having chatter, you get dimples on the surfaces of your contacts. That adds impedance, resistance. You can get heating inside the breaker. So it's very important that that breaker holds contacts closed, and then when the fault currents get too high that it can't hold the contacts closed for very long, it lets them open. The insulated case circuit breaker and the molded case circuit breakers are such that when the fault currents get high enough, there's not enough force on those contacts for all the magnetic forces due to the high fault currents. So we put in those breakers the ability for the magnetic forces to open those contacts when the fault currents are high enough, and when we know that I just can't hold those contacts closed without chatter. So all insulated case circuit breakers and all molded case circuit breakers will not, regardless of their size, do not fall under the requirements of 24087 in the 2011 version of the National Electrical Code. The only circuit breakers that this section impacts are what I call lovingly the double wide. And the reason I call that the double wide is because for these very high fault currents, these devices that do not have an instantaneous, I need a way to be able to hold those contacts closed under those higher fault currents up to 30 cycles. 30 cycles is a big impact from an incident energy perspective for that first piece of equipment downstream of these circuit breakers. And that could be that this circuit breaker is the main in that device, in that piece of equipment. And the way I get that done is I separate the contacts out. Instead of just having 3 contacts, I'll have 6. I put them into a breaker that is double the size, and I spread the magnetic forces out over 6 contacts instead of just 3. And then my springs and everything else can hold those contacts closed for up to 30 cycles, and then it's going to open up to the interrupting rating of that circuit breaker. So the only breaker that 24087 impacts in the 2011 National Electrical Code is the power circuit breaker that can have no instantaneous all the ways up to its interrupting rating. And if you have that circuit breaker, it tells you that where it's used without an instantaneous trip, documentation shall be available to those authorized to design, install, operate, or inspect the installation as to the location of the circuit breaker. So a one-line diagram that shows the location of these breakers is all you need to meet that documentation. Then it says where that breaker is utilized that does not have an instantaneous, you have to have one of the following methods to address the incident energy. One is zone selective interlocking, two is differential relaying, and three is going to be the energy reducing maintenance switching with local status indicator. The first one operates on a zone of protection. I have a downstream breaker and an upstream breaker. Say I have the main inside of a panel board or a switchboard or switch gear. In this case, it would be switch gear. I have the main inside of switch gear, and I have feeder and branch breakers that are also in that piece of equipment. Those devices are all wired together with a communications. They're basically like a 24 volt or whatever voltage signal, and it'll vary by manufacturer. The voltage signal. It's not a communication like with a protocol like Modbus or something of that nature. It's just a voltage signal. And how this operates is the upstream overcurrent protective device has to know whether or not it's going to trip based upon its programmed set points for the trip curve, or if it's going to ignore that trip curve and go without an intentional delay, based upon the short time pickup of that device. And I've got videos on this. Check them out on my YouTube site to go into the details of how zone selective interlocking works. So if there's a fault downstream of both overcurrent protected devices, then they all go as if they were planned. So any power any short circuit, any fault currents downstream of both of these devices, they will both trip based upon their trip settings. But if a fault occurs in between that main device and the first downstream device that are wired together, then the upstream device, when it sees the fault, it looks for the signal coming from the downstream device. If it doesn't see that signal, that means the downstream device does not see the fault current, because it also has a pickup value. When the fault current gets above its short time delay pickup, it sends that signal to the upstream device and says, hey, I see a fault. Don't trip automatically. Let me take care of it. But when the fault's in between, the upstream device looks for that voltage signal. If it's not there, it ignores its set points and goes without an intentional delay. And that's around 0.07 seconds for your average power circuit breaker. So 24087, you have to have one of those technologies. That's zone select. Differential relaying operates very similar. Differential relaying looks at all the currents going into a zone and then all the currents coming out of the zone. And if there's a difference, if I have two feeders downstream of a main and 100 amps goes in and each breaker is supplying 50, I'm good, because 50 and 50 add up to 100. The main breaker sees 100 amps going in, everything's good. But if I see 10,000 amps going in and this breaker over here sees a little bit and this breaker over here sees more, and they don't add up, then I know there's more fault current flowing in between somewhere, right? So if I have a fault inside the bus and my main breaker is supplying current and it's going outside of the path, the downstream devices don't see it. So now I have a difference between the two downstreams not seeing any current flowing out, but I'm still seeing 10,000 amps. That means there's a fault in between us, and differential relaying will pick that up and take it out. You typically see differential relaying on 4160 volts and higher. You don't see differential relaying at 480 volts. Zone selective interlocking, that's your differential at 480 volts. And then your energy reduction maintenance switch, that is a maintenance switch that when you turn it on, it basically puts takes that instantaneous, shoves it down to a very low value while that switch is on. So when you're doing work, if there's a fault, it will trip instantaneously as long as the arcing current is in that region. There's no requirements in the 2011 code for you to evaluate whether or not the technology will reduce incident energy. So that's a change. That's something that the next version of the code is going to have to look at. But right now, you have to have one of these technologies, and you have three options. There's an informational note on telling you what the energy maintenance switch is. Now, when you put that switch in its maintenance mode, an indicating light has to tell you that it's in a maintenance mode. And when you take it out, the indicating light has to indicate that it's not in a maintenance mode. So an indicating light that turns on when it's in maintenance mode and shuts off when it's not in maintenance mode, that's basically what the National Electrical Code requires. So very historical moment in the National Electrical Code, as another historical moment where now we have a 24087 that is looking for any circuit breaker that does not have an instantaneous to require an arc reduction technology. You have to identify where those breakers are. Single line diagram will get that done. And that's 24087. And that's any circuit breaker, AC, DC, regardless. And since it's in part 7, which is, if you look at 240, if you go up to 240. The scope 240.1, it tells us that parts 1 through 7 of this article provide general requirements for overcurrent protection and overcurrent protective devices not more than 600 volts. So this requirement of 24087 is in part 7, which only applies to 600 volts and less. It doesn't apply to a 4160 or a larger circuit breaker. But it doesn't say anything about AC versus DC. So if you have a DC circuit breaker, you need this technology. If you have an AC circuit breaker, you need this technology. If it's 600 volts or less, you need to look at this section. If it doesn't have an instantaneous, you're going to need these technologies. If it's greater than 600 volts, you're not in 24087. Because 24087 does not apply outside of anything greater than 600 volts. All right. Hopefully that helped. And that is 24087 as per the 2011 version of the National Electrical Code. Thanks for watching.